Hi class, this is number 2 in 10.3, sorry about that. Let me share my screen. A new beta blocker medication is being tested to treat high blood pressure. Subjects with a high blood pressure volunteered to take part in the experiment. 180 subjects were randomly assigned to receive a placebo, and 260 were assigned to the medicine. High blood pressure disappeared in 100 of the control and 132 of the treatment group. Tesla claims the new beta blocker medicine is effective at the alpha equals 0.01 level. So, yes, see, listed first in the null hypothesis has to be the first population. So is this a proportion? Well, they sure don't talk about a mean value at all. So I don't think it's a mean problem. So it's the only other one we talk about is proportion. So it's proportion, and they always put proportion 1 in this alternate on this left-hand side of the. So we always put P1 here if we're talking about proportion 1. And the other side here is going to be P2. And then now they say, and can you guys see that proportion that they said, 100 of the controls, which means the ones that received a placebo, 100 of the 180. So that's a proportion, right? Had a certain effect, right? And then 132 of the 260 had a certain effect. So you can see that that's a proportion. And it looks like, I mean, if this medicine works, they wanted to know, is the medicine effective? That means the proportion who have blood, it disappeared. The proportion that had the high blood pressure disappeared should be larger in the people that are getting the treatment. There's a larger proportion of high blood pressure disappearing. A larger proportion of people who had, say, their high blood pressure disappeared, or we measure their high blood pressure disappeared in the treatment group than in the control group, right? So a lot of times with these problems, I will, whatever one is mentioned first, and I kind of look at the way the test claim was mentioned. Like if they say 1 is less than 2, or population 1 is less than 2, then I will literally write that as my test. My less than symbol will be in the alternative hypothesis. So kind of listen for that, in the way they have listed it in the sentence. Usually the first one that's listed in the sentence, I use population 1. This one's kind of odd. They don't really list anything first, anything second. So let's go ahead and just say that, well, I noticed that they put, when they listed the people, say 180 subjects were assigned to a placebo, they are, just because they're mentioning the placebo group first, I'm going to just say that's population 1. And so let me write that down. It's important to kind of define your variable. Tell them, what is population 1? What is P1? It's important for yourself and important for the problem as a whole. So let P1 be the proportion of the control group or placebo group. That's the same thing. Control group is the one that receives a placebo. that had high blood pressure disappear? Okay, and then you let P2 be the proportion of the treatment group. That's the ones that are taking the drug group, drug taking group, right? That had the high blood pressure go away. Okay, so we clearly define the variables, and because if this drug is effective, then it has a higher proportion of people who had their high blood pressure go away. So I want my alligator's mouth to face toward the proportion of treatment in the proportion of those who are being treated with the drug. Okay, because I want to say that more people who, if people took the drug, then they're more likely to have high blood pressure go away, right? Or I want to say the proportion of those who are healed taking the drug is higher than the proportion of those who are healed who took the placebo, right? So I want my alligator's mouth to be toward the proportion of people taking the treatment. Proportion of people healed that were taking the treatment. Okay, so that's the area of my alligator's mouth. So let's just see how I'm going to go ahead and put this answer in, and then so as soon as I'm like this, so I'm going to call this, what is that? So if you look at where these arrow, if you make this into an arrow, then it's pointing to the type of test that we're doing here. So it's pointing to the left. So this would be a left tail test. But just in case they ask you that question, which they may. So there we go. That's what we want. And then the null hypothesis is always either equal. Always the equal sign. It's exact same variables and numbers and that you see in the alternative. The only thing different is the inequality symbol is either just equal or equal and opposite. So I'm just gonna say, I'm gonna hope that they're gonna accept equal. Okay, so let's just double check and see. I'm gonna submit this and see how they make sure that they accept this. I'm a little concerned because there's a few different ways to present this answer, and I'm hoping that this person who made this question took that into account. So let's just submit this part of it, and they like it. Okay, so the other issue, and I'm just going to double check, they should accept equal to or greater or less, greater than, whatever, this one. They should also accept that, and they do. Okay, so this is a really well done question that they would have accepted equal or opposite inequality in the null, or also just the equal. They would have accepted either one, which I really appreciate that they made both of those correct here in this problem. Okay, that's important because either of those would have been correct. I did want to mention too that I could have easily just chose that population 1 be the treatment group. I could have done these vice versa. And population 2 would have then been the control group. And if that was the case, like if I had switched this, which let's try it, if I would have switched it and said, okay, well, actually P2 is here and P1 is there, and then I would also have to switch the inequality symbol to make that still say the same thing. Well, hold on a second. If I just switch and I'm gonna let, okay, I'm gonna do this problem all over again. And so just, I'll switch it back to the regular in a minute. But let's just say for a second here that I think we want to keep P1 over on this side no matter what. I think they want P1 on that side because that's the usual typical. You put 1 on this side and 2 on the other side. However, what if I called 1 the treatment group and 2 population 2? What if I, said let that be the control group? Now, if I did it that way, then to make my null hypothesis right, I would want the alligator's mouth pointing toward the P1 because P1 in my mind is the treatment group, and I would want this to be the equals group. So technically, I feel like they should accept this as well, but let's see. So they do not like that. All right, so, and I didn't think that they would, but I am a little, worried about this problem because they should tell you, hey, let population 1 be the control group. The only indicator that I had a little bit in this problem that I should use population 1 for the control group was because they listed that population first when they first introduced it. Notice how they said 180 subjects were randomly received to have a placebo. So as soon as they were like, they listed that first and then the other group second, I thought, okay, that was probably, I just want to go with that being my population 1 and the other one my population 2, just so I can match their answer. And so you might want to follow that procedure. That seems to work pretty well for me. But technically, if you would have labeled your P1 and P2 just as I have labeled them, then technically this answer would be correct. This P1 larger than P2, because if a P1 is my population of my treatment group, then that's what we would want. So I feel like they probably should have defined P1 and P2 for you for this problem. But anyways, let's go back and let's do the less than symbol like it should be. And let's do it as a left tail test. I'm right tail. That's right. Yeah, I was right. Left tail test. The arrow is pointing left. Okay. So let's go through with how to solve the rest of this problem. So there is kind of, like I said, if you get this problem wrong, just email me and have me double check it. And you can kind of explain to me what your population 1 was, what your population 2 is, and then that'll help me. Okay. All right. So now that we have it set up like this, now we'll find the test statistic and the p-value and stuff like that, all the rest of the information. So we go with all of these proportion 2 sample tests. We do a 2 sample proportion test. So let me just like X out of these, and then we'll go down statistics tests, 2 sample Z test, 2 prop Z test. Okay. And they want the number is X1, which is the sample success count in the first sample. So that's the number of people who had your desired characteristic in sample 1. And so because we called population 1 the control group, that's the number of people in the control group that had lowered blood pressure. So let's go back over here. Oops. Oh, I don't think I ever switched these back to the way they were supposed to be. All right. So, okay, the number of people who had the medicine disappear in population 1, which was the control group, is 100 of the controls. So the 100 of the 180 had the high blood pressure go away. So I go back and I'm gonna input 100 for the success count of the population 1, and the 180 for the success count of population of that's the number sample size. And now I'm going to do X2, the number of people with high blood pressure go away in the treatment group over into the number in your treatment group, sampled in your treatment group. All right, so that's going to be the 132 over the 260. And hopefully, you know, when it says here 260 received the medicine, the people who are receiving the medicine are the treatment group. So when they say 132 of the treatment group, they mean 132 of the people who received the medicine, which is the treatment group. And the people who received a placebo, that's the control group. So just so you know that. Okay. Now all I do is just run this test. And now I go back to my the alternative hypothesis, and I notice that the alligator's mouth is facing toward the right. You know, the alligator's mouth is open toward the right. That's just to help me figure out which, and I need to match this exact symbol to the one I'm going to choose over here. So I'm going to choose this alligator's mouth is open the same direction as this alligator's mouth. So this is the p-value that I want. There we go, the 0.83. So the 0.83. So let's just double check. Oh, and then they also just spit out the Z statistic, the 0.98887. So we have the 0.9887 is the first answer here, test statistic. And then the second answer is the 0.8306, that p-value right here. And then, so those are our answers, and they say the test statistic. Okay, here's something different and new that maybe you guys are not, that I did not go over too much, is that they ask the test statistic, is it in the critical region? So there's a second way of kind of doing these tests. And the second way of doing it is this is a right tail test. So this difference, so we found the difference between the two samples and the two proportions. And this difference is out in the tail over here. Actually, it's not. It's more. It's a larger value. It's like over here somewhere, because the p-value is 0.8, so it's practically all of the area under this curve, and all the area is 1, but this is most of the area under the curve. So this is where our test statistic 0.988 is. This is also the value they got by kind of seeing how different the two proportions were. Now, in a left tail test like this, the critical region is a region such that, let me get another color, such that there is whatever the alpha is, there is 0.01 area to the left of that value. So this is our critical value. I'll just see it's the critical value. And to find that critical value, you could just do inverse norm, because this is a Z distribution, inverse norm, and you just do 1 minus, actually for this particular problem, you always need to enter the area to the left, but the area to the left is already there. So this is, so inverse norm of just the area given. In the left tail test, you just put the area, 0.01, I'm sorry, of level of significance. I'm entering the level of significance here. And then I put I believe I put the mean and standard deviation of the normal distribution. So this gives me the value along the x-axis under the Z distribution such that there is 0.01 area under the curve to the left. And I could do that. Let me do that calculation really quickly. So you do normal distribution on here. You do on your TI-84 calculator, you just do inverse norm, you do distribution, then inverse norm. This one I have to do normal distribution. And then I do this 0 and 1 because that's the Z distribution. The mean is 0, the standard deviation is 1. So that's just because it's a Z distribution. The sampling distribution of the population portion is a Z distribution. So it's just then what I do is I close off that parenthesis, and then I'm going to do stats and then inverse here, stats, distance plots, and inverse CDF. And then into that, I'm going to put the area under the curve to the left, so 0.01. That's the alpha. That's this level of significance. And then I put, and then I believe that's all I have to put. Yeah, and then there's my answer, 0.232. So what that's telling me, and this is a long involved answer. Was it -2? -2.32. The critical value is -2.32, and it's literally saying you have -2 standard deviations, 2.32 standard deviations below the mean. When you have that value along the x-axis, then the area under the normal distribution to the left will be 0.01. And my picture is probably not to scale. It's probably a little bit further to the left than that, right? This critical value is probably further to the left. It's probably like over here. Because that's pretty small. This area is 0.01. And this critical value is -2.32. And so this -2.32 is a cutoff value along the x-axis. And they're saying any value that's smaller that's further to the left on the number line, that would cause us to have a p-value that we would reject, because the p-value is going to be an area smaller than the red region. Any value that has a test statistic that we calculated here, 0.9887, test statistic smaller than negative 2.32. So like if we would have had negative 2.5 as our test statistic, then we would say, hey, the test statistic is in the critical region, because any value to the left of negative 2.32 is in the critical region, because any value in there, any test statistic in there, for example, if I just had, this was my test statistic that I calculated. Let's say that the test statistic was a negative 2.5. Then see the area under the curve to the left of negative 2.5 would be smaller than the area under the curve to the left of negative 2.32. And because that area is smaller, then the p-value would be smaller than alpha. And so automatically, any value that's less than any hypothesis test that would have, well, in this situation, any sample that would cause us to have a any two samples that would cause us to have a test statistic smaller than negative 2.32 would cause us to reject the null hypothesis. So this region, so like just cut it off right here. The region to the left of this critical value is called the critical region, because any test statistic in that region, once we get this test statistic is less than negative 2.32, then we would reject the null hypothesis. And that's another way of doing this test. And we don't even have to go to all the work doing a p-value. If all we have to do is calculate this test statistic, which you would just use a formula to calculate the test statistic, and you would just compare it to the critical value. And if it's smaller in a left tail test, if the test statistic is smaller than your critical value, then you reject the null hypothesis. And that's another way of thinking about it. So like I said, this is the critical region. And anything would have in that region would have a p-value, of smaller than alpha. So we would say the test statistic in this situation, since the test statistic is not to the left of negative 2.32, it's actually to the right. It's right here. Our test statistic is over here, the 0.9887. It is not in the critical region. And then the correct decision here is we fail. We fail to reject the null hypothesis. Right, just a second here, like we never say we accept the, we would never say that we accept the alternative, or, well, I'm sorry. We would never say that we accept the null hypothesis. And we don't actually, when we make a decision here, we don't say we accept the alternative hypothesis either. We really just say this in terms of the null hypothesis. Do we reject or do we fail to reject the null hypothesis in that decision making there? Okay, so that's why we choose fail to reject the null hypothesis here. And that's a little misleading, because if we fail to reject the null hypothesis, that means kind of we have evidence to support, or we sort of kind of like saying we're accepting the null hypothesis, but we're not really accepting the null hypothesis. That's just. And for the same reason that in the court of law, when we have a final decision made in the court of law, we always say the null hypothesis in the court of law, the thing that we accept as truth until proven otherwise, is that the person is innocent. So let me write that out. So the null hypothesis in a court of law is innocent person, right? Innocence, innocent. Now, the alternative hypothesis is guilty. Now, when the judge has said, I made my decision, They never say, therefore you are innocent, because that's a really strong statement for anybody to say to anyone. You could easily have a little bit of guilt, or a little bit of causing the accident. What we always say in our decision is either the null hypothesis is true, or I'm sorry, we either say we don't, we just well, in our final concluding statements, we either say the evidence supports the alternative hypothesis, or the evidence does not support the alternative hypothesis, but we never say, hey, the person is innocent. So you always say your final statements as I have evidence to support the alternative hypothesis, or I have evidence not to support the alternative hypothesis. And we always say whether the decision here is always to reject the null hypothesis or to fail to reject the null hypothesis. That's the first decision that we have to make before we get to the final conclusion. And so the next step is, the correct summary would be, if we fail to reject the null hypothesis, then we fail to have evidence. There is not enough evidence. So those two go together. Fail to reject the null hypothesis, then you fail to have enough evidence. So we say there is not enough evidence to support the claim that, and they should have here just restated the alternative hypothesis, that the new beta medicine is effective. So that's what we want. So let's just double check that they like all of these answers. And so this looks good. Email me if you think that you probably did this problem correctly and you don't know why it's like marking you wrong, because it could be just, unfortunately, it could be like a glitch in this problem. I already sort of see a problem that if you mixed up your populations, which they don't tell you how to correctly label your population. So I could see how you could, maybe it marks you wrong and you didn't do it wrong. So if you have any questions about this problem and you're not getting it right, just go ahead and email me. All right, have a good day. Bye, everyone.